This is a short list of the most commonly inferred resources. For example, the shift register LUT is commonly used to build delay elements or pipeline stages. It is easily inferred, but with the limitation that the outputs cannot be reset and its contents cannot be initialized. So if a user were to code for a shift register with a reset, there is no way any synthesis tool could infer the SRL. There would also be no warning or error message sent by the synthesis tool, since the tool would think you wanted to build a shift register with your standard flip-flops. There would be no error in that. Likewise, the implementation tools would not give a warning or error message, since the netlist made by the synthesis tool would reference flip-flops, and as we know, there's nothing wrong with that. You should also note that even if you were to build an appropriate shift register component, your synthesis tool may still require you to place an appropriate attribute in your HDL that will tell it to map to the SRL primitive. So one of the most helpful skills a designer can have is to have enough experience with their synthesis tool to know the appropriate attributes and its appropriate coding style limitations for that synthesis tool. One of the best ways to determine how to infer a resource is to go to support.xilinx.com and open the XST user guide. Now this is also associated from the ISC software. You can get it there from the help menu as well. And then do a search for SRL coding techniques, and you'll find examples of how to infer the shift register LUT. Now this user guide provides numerous examples of a wide range of dedicated architecture resources in the FPGA and shows you how to infer the best FPGA resources. So be sure and check out the XST user guide. Now most designers are instantiating memory resources, I/O standards, including SerDes functionality, and clocking resources on every design. That is because there is just so much flexibility with this FPGA architectures that the synthesis tools just can't build a tool that will infer all the possible configurations that a customer might use. So you're probably better off planning to instantiate these resources from the beginning. As I mentioned earlier, we suggest that you keep your instantiated components in one location. Now most designers place the Xilinx specific instantiations at the top, or one layer down or one level down, but never more than that. This makes it easy for the user to locate and maintain the design and port your code to another device family or technology later if necessary. We also recommend keeping your pin assignments and pin attributes in your design's UCF files so all designing specific constraints are removed from the HDL. This makes your code more generic. Another instantiation option a designer has is to use the VHDL configuration statements or put wrappers around each instantiation. Now this will maintain the design hierarchy and still make it easy to swap instantiations if your design migrates to another architecture. Xilinx recommends that hierarchical optimization. Now that is a standard synthesis option that allows users to optimize combinatorial logic across a hierarchical boundary. Now we recommend that this hierarchical optimization be turned off. This is because synthesis tools will change node names and change the logic optimization on nodes that users will often want to simulate, probe, debug, or analyze in some way. Allowing this optimization will sometimes make debugging nodes on a hierarchical boundary much more difficult. So in general, we tell our customers to leave this optimization across hierarchical boundaries off and only use it later as a final last-ditch effort to gain time and closure. Fortunately, most customers don't get this desperate, but we like to mention the proper use of your synthesis tool here so that you have the ability to debug and simulate nodes later. Now, all synthesis tools will default to not allowing optimization across any boundaries. However, if you choose to enable this optimization, only enable it across the boundary associated with your timing critical path and never allow it to be used globally. Maintaining your design's hierarchical boundaries yields numerous benefits, as I mentioned a moment ago. It makes it easier to locate nodes when you are simulating probing with ChipScope, for example, or simply reading a synthesis or timing report. However, what many customers don't realize is that it also enables floor planning and the use of incremental design flow. Incremental design allows users to maintain the place and route solution found for part of the design and only repeat place and route on components that fail to meet timing or have changed logically. Note that most experienced designers know that for optimum speed they need to make sure their timing critical hierarchical boundaries have registered outputs. This is a pretty standard way for users to tolerate a high fanout net that a component might be making, or if they know the placement of the destination logic might be far away. But commonly, when a designer makes a purely combinatorial piece of logic, adding a register can easily be accomplished by converting the component to a registered component. If the component already has its outputs registered, then optimizing across a hierarchical boundary will have no effect, since logic optimization will not remove the register. You may recall that I mentioned it's important to be aware of what your synthesizer will generate depending on how you code a piece of logic. The first component we're going to look at are muxes. If you build a mux with if-then statements, synthesis tools will almost invariably build logic into priority encoders. Now likewise, if you build it with a case statement, the synthesis tool does not give any signal a priority. So if you build a mux with if-then statements, note that the timing critical signal, that is the signal on the first if statement, ends up in the last logic stage. This signal will have to go through only one logic level and have the shortest delay. This is perfect for the case when you need one of the inputs to be faster than the other inputs. You may have also heard about that unintended latches or complex clock-enabled equations can be synthesized when your if-then or case statements do not cover all possible conditions. Now, fortunately, synthesis tools warn users when they are building latches, but they do not warn when the long clock-enabled equations are being built. That is why it is important that you verify for yourself what is being synthesized by your HDL. To do this, the best tools provide schematic viewers that show when this is happening. So this example shows you that the if-then statement construction of a mux builds LUTs in series. Now, it is very important that you understand that having these LUTs in series produces long delay paths. Just look at the do_e input. Its path to the output requires 4 LUTs and 3 net delays to be traveled before the output would be accurate. So this and the do_c paths are the longest and will be the most timing critical paths through this component. Conversely, the critical_sig path will only have to travel through 1 LUT. This is of course much faster. The component's construction was all inferred by the synthesis tool when we coded the mux with if-then statements. Note that the order of the inputs to the if-then statements, the most timing critical is listed first, followed by each of the lesser critical signals, and ending with the least critical inputs in the statement. Now, if you build with nested if-then statements, be sure and watch your timing on your inputs because the LUTs can cascade easily. Always be sure in this case to put the timing critical signals first in your HDL. However, the best solution is to build the component with a case statement as much as possible. Case statements do not build with LUTs in series and tend to build the LUTs in parallel, which is dramatically reducing the number of logic levels. If the last example was constructed with 4-input LUTs, it would require only 2 logic levels. Recall that the function had 9 inputs, which would require 2 LUTs in series and a total of 3 LUTs. So see if you can make that work and replicate what we expected and how the difference would come by using a case statement. Case statements are almost always the way to go when muxing logic. However, be sure to define all outputs in all branches. Otherwise, this will produce a latch and a warning message. To do this, we recommend using a default statement before the case statement. Case statements used in a register process or always statement can produce a long clock-enabled equation. So likewise, we recommend using a default statement before a registered case statement.